Hello and welcome to my applied presentation for graph theory. Today we're going to be looking at the stable matchings algorithm, and what this problem what this algorithm really solves is if we have a community with n men and n women, and this is an important idea that the number of men is equal to the number of women. What we really want to do is to pair off these men and women in the best possible manner. And we'll talk about what that best possible manner really implies as we get going. But I do have a few what I would consider to be time-sensitive assumptions. This algorithm was written in the 1960s, and so some of these assumptions are very what I consider to be time-sensitive. This problem is all about taking these men and women and marrying them and making them a pair that will last for a while. So all these marriages will be assumed to be man-woman pairs. It's not going to work if we let men marry other men or women marry other women. Although you could write it as such, it would just it would take a little bit more work. In this case, all the men are going to be the proposers. Again, very time sensitive that men will be proposing to women. And again, somewhat very time sensitive in my eyes that women would rather be with anyone rather than no one. Okay? So, if a woman gets proposed to and her only proposal is from the smelliest guy in town and her least favorable man, she's still going to accept that proposal if that's her only one. So, let's go ahead and take a look at this. Some of the definitions that we're going to have, the first thing we see is a pair. And a pair is just, via the algorithm, an assignment of man Y and woman A. So they are matched together there. By the end of the algorithm, if they are still a pair, they're going to be getting married. An unstable pair, which by the sense of the name is a bad thing, is an assignment in which man X and woman A prefer each other, but are paired via the algorithm to different partners. So these two groups here, these two pairs, have been paired up via the algorithm, but woman A prefers man X over man Y, and at the same time, man X prefers woman A to his current assignment, or his, I should say his final assignment, woman B. So in the sense of what we want to find a stable matching that has none of those unstable pairs. And so throughout the course of this, what we're really looking to avoid is any woman that prefers another man from a different matching at the same time that man prefers that woman. Okay? Prefers that woman over his current matching, over his current pair. Okay? The way we're going to do this is, considered to be the proposal algorithm, or the Gale-Shapley or Shapley algorithm, however you prefer to pronounce it. And the input for that algorithm is that all the men in the subgroup and all the women in the subgroup rank the members of the opposite sex from most attractive, or most want to be married to least. So in this case, and you can look at all of them, we're going to be using these two groups of men and women in our example today. But Alvin prefers Charlie to Becky to Donna to Adriana in that order. And at the same time, Adriana prefers Alvin to Bob to Cameron to Donald. And again, in that order. So what this algorithm does is at every step, every man will propose to his highest ranking woman on his list who has not previously rejected him. So, and in practice, what that's kind of going to look like is in the first round, we'll see that Alvin will propose to Charlie, Bob will propose to Charlie, Cameron to Becky, and Donald to Donna. And then what happens in the algorithm is where the kind of the money is made, I guess. Each woman, if she receives only one proposal, she's going to accept it. And that goes by that assumption that a woman would rather be with anyone rather than no one. And then if a woman receives more than one proposal in any round of this algorithm, she's going to reject all but the one from the highest man on her list. So if Becky, for instance, receives a proposal from everyone, from Donald, Bob, Alvin, and Cameron, she's going to reject all of them but her top one, which is Donald. Similarly, if in one round Donna was proposed to by Donald, Bob, and Cameron, she would reject Bob and Cameron and only take Donald's proposal. Okay? And something that I might get a little bit mixed up is that in just a single round, Donna will tentatively accept Donald's proposal as opposed to permanently accepting it. She would permanently accept it if the entire algorithm was complete. Your book is going to say that she would say maybe to Donald until the very end of the algorithm, in which case she would formally accept that proposal. So let's go ahead and look at an example. We're going to find homecoming dates for these for these 8 people, 4 guys and 4 girls. And let's go ahead and run through the algorithm. For step 1, we're going to have all the guys, as I said, propose to all the girls that are highest on their list, since there's been no rejection so far. So Alvin will propose to Charlie. So Charlie gets proposed to by Alvin. Bob will also propose to Charlie. Apparently Charlie's the popular girl. Cameron will propose to Becky. And notice that she's going to tentatively accept that since it's the only proposal that she gets. And Donald will propose to Donna. Now what happens in this step is that Charlie received 2 proposals, so she is going to reject Bob's proposal and tentatively accept Charlie's proposal. So, tentatively accept Alvin's proposal. So Bob gets rejected, but at the end of round 1, we have some tentative proposals, and Alvin and Charlie so far are going to go to the dance. Cameron and Becky are going to go to the dance together, and Donald and Donna will go to the dance together. But we're not done, so those may change. What we need to do for second round, there's only one guy that's not going to the dance with somebody, and that's Bob. He's going to propose to Becky. Becky, seeing that Bob is higher on her list than Cameron, will tentatively accept his proposal, in the meanwhile rejecting Cameron's. So Cameron is now single and looking for a date. Essentially, where this algorithm is a little bit different than how we see it through the example, when Bob proposed to Becky because he didn't have a date, Cameron also proposed to Becky. So Becky got two proposals, and she then rejected all of them but the top one. Okay. At the same time, Alvin still proposed to Charlie, and Donald still proposed to Donna, and that was their only proposal for that round, so they tentatively accepted those proposals. So at the end of round 2, we see that Alvin's still going with Charlie, Bob is still going with Becky, and Donald is still going with Donna for the time being. The next round starts with Cameron looking for a date, since he's the only single guy so far. He's going to propose to Charlie. Cameron is the lowest one on Charlie's list, and again, Charlie also receives her proposal from Alvin, and she prefers Alvin to Cameron, so she's going to reject Cameron. So this is a round of the algorithm, even though nothing has changed. The same the same sets of couples are still tentatively going to the dance together. Lastly, Cameron is going to propose to Adriana. Adriana, receiving no other proposals, will tentatively accept. And since all the men have found their dates, found a willing woman to go to the dance with them, the algorithm is over. And we get the final pairings, sorry about that, we get the final pairings of Alvin going with Charlie, Bob going with Becky, Cameron going with Adriana, and Donald going with Donna. To just make sure that this produces a stable matching, we see that Alvin is going with Charlie. That's his top choice. So he doesn't prefer anybody else over Charlie. And at the same time, Charlie is going with Alvin, who's his top choice, and thus doesn't prefer any of the others over Alvin. At the same time, Bob is going with Becky, which isn't necessarily his top choice, but Charlie already refused him. So he's going with what's left as his top choice, because you see his list actually gets shorter of the possible women that he can go with, because he cannot re-propose to somebody who has already rejected him. So Bob wants to go with Becky, and we look at Becky. Becky is only received in the final of the final round of the algorithm, has only ever received proposals from Bob and Cameron, and she prefers Bob over Cameron, so they're going to go to the dance together. Cameron got rejected by Becky and Charlie, falls back to Adriana, and Adriana, receiving no other proposals, goes with Cameron. And finally, Donald proposes to Donna, which is his top choice, and Donna did not get a proposal from Alvin, so this is what's left as her top choice. Okay. Another way to see that this is a stable matching is that Adriana would much rather go to the dance with Bob or Alvin, but Bob and Alvin both have Adriana lower on their list than they have the people that they're going to the dance with, and Charlie and Becky. So this does produce a stable matching, and that's actually the proof that we have, or the theorem that we have, is that the proposal algorithm produces a stable matching. The first step is just to say that it ends with some sort of matching, and we saw that happen, that being because the lengths of the lists for the potential mates for the men constantly decreased. So as men got rejected, their list decreased, and that tells us that eventually there's an end as the group of men and women are finite. There can actually only be n squared rounds of these proposals. So if you were looking at computing time for this algorithm, it would be n squared because there are n men and n women, when in all actuality it ends up usually being a lot faster than that. So to prove that the matching that we have is actually stable, we're going to assume the contrary, and we're going to say that we're going to suppose that the matching is not stable, looking for a contradiction. So we're going to let XA be an unstable pair. So what we're really saying here is that throughout at the end of this algorithm, we end up with kind of how we saw in the beginning. We have man Y matched up with woman A, them going as a couple to the dance, and at the same time we have man X with woman B, and they're going to the dance, but these two simultaneously prefer each other over their assigned pairing. So that is, by definition of unstable pair, that's what we're going with for our contradiction, or trying to use that to find our contradiction. But what that means is that man X, since they're not paired together, he never proposed to woman A. And the reason for that is that in every round of proposals, remember that every round of proposals has man X proposing to every woman that's the highest on his list that has not rejected him. So that in and of itself is almost a contradiction, in that if man X really would prefer to go with woman A, he would have run into that pairing before the pairing that he's currently going with, which I assumed was this woman B for lack of notation. But to really drive this contradiction home, man X would not have proposed to woman B without earlier proposing to woman A, really meaning that man X's list would look something like, somewhere along the road he would hit woman B and then later woman A. So he would not, this would not actually be an unstable pair, because for that to be the case, A would have to be above B, and since he got paired up with B prior to the end, he actually prefers B to A. So this is not an unstable pair, which means that this matching is not unstable. Or sorry, let's just say that the matching is stable. There is a real-time application of this algorithm that has actually been going on since before the Gale-Shapley algorithm really existed. It wasn't finalized, I would say, until it was actually finalized in the 1990s. But one thing that we really notice out of this algorithm, and let me back up a ways to find that. One thing that we notice from our example is that all the men did the best they could in finding dates. This is actually the best possible outcome of a stable matching for the men. And the reason I say that is because it's actually the worst possible outcome for a stable matching for the women. You could run this whole process with the women being the proposers, and in this actual instance, in this ranking of men and women by men and women, it's actually the same whether you do it from the men proposing or from the women proposing. But the women actually got stuck with, you would say, names that were farther down on their list. And that is just the nature of the proposal algorithm, that the proposers actually get the better deal. Now, where this comes into play with with what's called the match, or the National Resident Matching Program, this matches doctoral candidates, people that want to be medical doctors, into the hospitals where they will do their residency program. So this program, the match, actually runs the Gale-Shapley algorithm to put residents into hospitals. Now, when this first came out, the funny side of this and why this didn't actually get finalized until the 1990s is that when it was first put out there, it had the hospitals as the proposers, or in our example, it had the hospitals as the men. And so what that would end up doing is it would leave open spots in hospitals where some of the resident candidates actually wanted to be in that hospital over the one they got placed into. Okay, so they ran the algorithm for a long time with the hospitals as the proposers, and that put residency candidates into hospitals that they didn't prefer as much as the ones that they wanted to be in. So in the 1990s, this program actually got switched around to make it a resident first, or a resident proposing algorithm, where the residential candidates took on the assignment, or took on the persona of the men who were proposing to the women in our example. So it's a good thing that it got switched around, because now there's a lot more happy residents out there that are in the hospitals that they wanted to be in. Thanks for tuning in, and we will see you later.